Good evening and welcome to our today's webinar. For those who has missed our previous parts, my name is Adam and I work in Smarting department.
And my name is Jurek and I work in the Professional Services department.
Today we will continue extending our AVPN topology and we will show you how can it be used to interconnect cloud, IoT or branch offices. Please note that in the YouTube description there is Slido link where you can ask questions, and those questions will be posted at the end of the webinar, and that will be time we will be answering them. Okay, first a few words about our company. Decodeline was founded in 2011 and now we have about 200 people on board and we are still growing. We are no longer a startup obviously, but we continue to keep its spirit, a culture of agility, innovation and adaptability. Most of our team is located in Warsaw and Gdańsk. However, in current year, we work mostly from the home. So, all that said, we frequently work with the modern AVPN-based DC, often with some SDN on top of it. Having some experience in our team got us thinking, how can we improve this architecture? Can we speed up changes in DC? Can we extend it? Or what can be done better? Previous and today's presentation are all about that. So far, we have shown you how we can use BGP Auto Discovery with the IPv6 connectivity to create fully automated and scalable DC. Then we use that DC to interconnect different resources such as Kubernetes, VM, containers, all together using AVPN and FRR. What goes left is a world outside of the DC, means public cloud, branch offices, IoT. We will try to cover those during this webinar.
Yes, but first off, let's take a short recap and see what we have talked about on the first and on the second webinar. So we have shown that we can use IP version 6 link local addresses, so we do not have to manually configure each of the addressing on the links between the networking devices and also on connections to servers. We have also showed that we can use neighbor discovery, so the BGP session can be automatically established even if we do not explicitly configure neighbors. We have used FRR on the servers, a routing daemon, which is capable of running BGP, and thanks to that we are able to automatically advertise all of the IP addresses that are configured on the servers in our data center. And even though we were using IPv6 addresses on the connections, we are still able to use IPv4 for communication with applications, with services, with whatever we are running in the data center. And also, thanks to BGP, we have achieved load balancing through ECMP and very fast failover thanks to BFD protocol. Now, BGP protocol was also required for us to provide EVPN, and this was the point of the second webinar. So here we had an IP fabric which provides layer 3 only connectivity, and we were able to still allow for layer 2 communication between VMs, between containers, through the use of VXLAN tunnels. However, we didn't want to use to manually configure VXLAN tunnels. We wanted them to be automatically configured, established, and also for the MAC addresses and IP addresses reachable to also be advertised through some automated means. And this was the role of EVPN. And at the same time, we were also able to provide multi-tenancy, so we were able to separate the applications and services from each other, and it is perfectly possible to use VRFs to have several customers using our infrastructure without them being able to communicate with each other unless we want them to. So this way we were able to create a heterogeneous data center in which containers, VMs, some physical servers, some laptops, different kinds of resources were able to speak with each other at layer 2.
Okay, today we try to show what can we do next. We can try to show how can we connect various resources outside of the data center. To do that, we'll create a hub, and you will use that hub along with the WireGuard tunnels to attach different resources from the internet. Of course, we'll also cover how to connect from the inside of the data center, from the VMs to the internet, how to route between those networks via a firewall, which knows nothing about the VPN. We'll try to extend the VPN to the IoT devices as well to the branch offices with the layer 2 extensivity or layer 3 as well.
Okay, so first off, let's get started with a technical topic that is routing between overlay networks. And if, in truth, this is something that we have already used on the second webinar during the demonstration. However, we haven't talked about it in detail. And the routing between overlay networks is very similar to what we know about routing between VLANs. However, here we have a device that is connected to 2 or more overlays. It has some interfaces attached to it, and it has IP addresses configured in this example to the green and to the blue overlay. So if it receives a packet in a VXLAN tunnel that belongs to the green overlay, it will be able to de-encapsulate it, look at the IP header, see the destination IP, which is in the green overlay, so it will encapsulate it again in the other VXLAN and forward it to the destination server or the destination virtual machine. Now, this can be done in software on Linux without much problems. However, this capability in case of hardware devices is not available on every data center switch. So keep in mind to check datasheets whether or not they can act as a VXLAN layer 3 gateway, because this is required for this routing capability. Now, what would happen if a server that is connected to only one of the overlays received a packet destined for the other overlay? So here, for example, server 3 would have to check its routing table, and it could actually find a route to the destination overlay. This is because EVPN allows to advertise not only individual MAC and IP addresses, but it can use type 5 routes. Over here, yeah, it can use type 5 routes which allow to advertise whole prefixes. Server 1, server 2 and server 4 will advertise that they have reachability to this subnetwork 10.0.2, and this information would be available at server 3. So if server 3 receives such a packet, it would just forward it to one of these servers using a VXLAN tunnel. What you can also see on this example is that the servers have interfaces configured with the same MAC address and same IP address, every one of them over here. And this allows for the resources connected to an overlay network, for example virtual machines, to use the same MAC and IP address as the default gateway. So, for example, if a virtual machine is migrated from one server to another, it can still use the same gateway without any ARP requests as soon as it is migrated. Okay, and one last thing on this slide is the fact that the communication between overlay networks can also be restricted. So we do not need to provide connectivity between each and every overlay in a given VRF. We can use routing policies to filter some of the routes. We might also use stateless ACLs or some stateful firewall policies on our devices in order to restrict the traffic. Now, this is provided that the layer 3 gateway is capable of doing that. All right, and finally, we can also use some advanced configurations so we can steer the traffic through, for example, a physical firewall or some dedicated VM that acts as a firewall, and this way also do some better, deeper inspection. Okay, right. So we can route between the overlays. Now, what about communication with the physical network? Well, by default, it is not enabled. It is not possible. What we need to do is we need to use either a layer 2 gateway or a layer 3 gateway. Now, a layer 2 gateway is a device that is able to stretch an overlay network onto a VLAN. So this is something we have used as well before, and it was the situation where we connected a bare metal server that didn't have any routing daemon running through leaf switches to an overlay network. And we can take the same concept and extend overlay, for example, to a firewall, where this firewall might be further connected to the rest of the physical network or the internet. And the firewall or the device that we connect to in the underlay doesn't need to know anything about VXLANs, EVPNs, and so on. Now, the issue with this L2 gateway is the fact that usually during the configuration, the mapping between an overlay network and the VLAN is 1-to-1. So if you want to extend 50 overlay networks to the physical, to have physical connectivity with the physical network, we would need 50 VLANs. So basically, this is not a very scalable approach. And in those situations, we can use the VXLAN L3 gateway. So the thing that we have shown on the previous slide. Now the only difference here is that the L3 gateway will be connected to a physical network through one of its interfaces. It could be multiple interfaces if you wanted to provide redundancy. Okay, so looking at this scenario, we want to provide connectivity with the internet. So in order to do that, the L3 gateway will advertise a default route. And this route will be sent to to all of the other routers in the overlay, so server 4, server 3, and server 1, using EVPN type 5 routes. So thanks to that, the servers will know that whenever they need to forward traffic in the direction of the internet through the default route, they will send it using VXLAN to the spine, and spine will de-encapsulate the packet and send it in native format to the underlay network. Now, in the other direction, connectivity from the spine to the overlay network is also based on these type 5 routes. So the servers will advertise information that they are connected to this prefix, but if appropriately configured, they can also advertise individual IP addresses of devices that are connected to them. So VM1 is connected to server 1, so server 1 will advertise the IP address assigned to this virtual machine. So thanks to that, the spine device, if it wants to send packets to VM1, it will know that the best route to this virtual machine goes through server 1 device. And this way we can achieve optimized traffic flows. The last thing on this slide is the network address translation. So if we want to reach internet from private subnetwork, obviously we need to use NAT. And this NAT can be done on the spine device, on the L3 gateway, as long as this router is able to support it. Or it can also be done on a device somewhere along the way to the internet, for example, on a firewall. Alright, and we can also restrict the connectivity using routing policies, ACLs, and stateful firewall, just as in the scenario when we are routing between overlays. Okay. Now, the third topic that we need to mention before we move on is tunneling traffic through some untrusted networks, such as the internet. In theory, this shouldn't be a problem, because VXLAN is based on UDP, and UDP is generally allowed on the internet without much restrictions. The problem is the size of the packets. So the maximum transmission unit on the internet is 1500 bytes. This means that if we have large frame that is encapsulated inside of a VXLAN tunnel, we need to add the overhead of an IP header, UDP header, and VXLAN header. And it is quite often with large frames is that the size of the encapsulated packet will be over this maximum MTU. And this would be especially true if we are using jumbo frames within our data center locations. So basically, in order to forward such big packets through the internet, one of the devices will need to perform fragmentation. So it will need to splice the packet into several fragments that will fit inside of the MTU and forward them to in the direction of the destination. And this is something that is natively supported by IPv4, by IPv6. It is quite commonly used, but there is a restriction that is introduced by VXLAN standard. And it basically says that VTEPs, unfortunately, cannot fragment VXLAN packets. Also, the destination VTEP may silently any fragmented VXLAN packets that it receives. So the solution here comes from this sentence from RFC. Intermediate routers may fragment encapsulated VXLAN packets, which basically means that if we want this solution to work, we need to perform fragmentation and reassembly on the devices somewhere between the VTEPs, somewhere between the VXLAN endpoints. And this is perfectly doable. Now, if we want to have a full picture, we need to mention also that fragmentation in general is not recommended. This is because it does require some extra use of resources at the devices that are performing the fragmentation and reassembly. It will also lead to slightly lower throughput. This is because if we have, for example, 10 fragments, then we need to attach an IP header to each of these fragments. And if we had only one big packet, then we would have one IP header. So we will have an extra overhead which will lead to slightly lower throughput. Also, we might see additional latency. This is mainly because of reassembly, where a device will need to wait for all of the fragments of the packet to arrive, and only then it will be able to put it back together and send to the destination. So it will take a little bit of time, which might be visible. There are also some more elusive issues that are summarized in RFC 8900, and if you do decide to use this solution, this would be a good lecture just to make sure that you do not fall into some corner cases where fragmentation might be problematic. But we do not want to discourage you from this solution. It is actually quite good, quite possible to transmit VXLAN packets through the internet. And fragmentation is very commonly used on the internet right now, and the prime example of that would be IPsec, which also relies on fragmentation to tunnel large packets through the internet. Okay, and one last thing when it comes to the topic is the fact that VXLAN doesn't in any way obfuscate the transmitted data. So the information is tunneled in plain text, and anyone who is able to capture the traffic would be able to read it. So if we want to secure the traffic, we will need to use some form of encryption in order for it to be safe. Now, in case of data center scenarios where we want to encrypt traffic within data center or between data centers, we might want to use layer 1 or layer 2 encryption. This would be possible. However, when we are talking about encryption through the internet, we need to use a layer 3 encryption or some higher layer form of tunneled traffic. So we could use, for example, IPsec, we could use a WireGuard, we could use OpenVPN, and there are several other solutions that could work here as well. What we want from this layer 3 or higher encryption is that it is usable over the internet. It doesn't require specialized hardware, so we would like to be able to run it on a normal CPU. Without any ASICs. We would want it also to be able to suit wide range of connectivity scenarios. So for example, we want this encrypted tunnel to work over network address translation, which is relevant for IoTs and edge computing. And finally, the encrypted tunnel solution needs to be able to handle this fragmentation and reassembly, because usually these devices will be performing these tasks. Okay, and with that, we actually have all the toolset that is required to talk about further topics, which are the cloud and the branch and IoTs and connectivity to them.
Okay, let's start with the cloud. Before we start describing our approach to the cloud, which will be based on AWS, let's summarize why do we think it's a good idea to do that. I mean, why not to use the native cloud resources such as AWS VPN with IPsec and BGP? In theory, they are doing exactly the same thing. They are stretching data center to the cloud, but they are doing just that and nothing more. The deeper you dip into the network or to the cloud products, the more issues you will find. Let's summarize the issues that we are aware of right now. For example, in a public clouds, we have no layer 2 working properly, which means you can find proxy ARPs, you will find that no custom routing between VMs will be working. For example, on GCP, you will find that interface has assigned 32 IP masks, which means there will be no ARPs at all and all traffic will be routed to the gateway. There will be no multicast in layer 2 or layer 3. There will be very limited IPv6 support. Some clouds does not support it at all. Some clouds support it only in selected locations. So IPv6 is also an issue. The native solution, the native VPN, can be very pricey. For example, on Azure, it's quite expensive. There is limited protocols that can be run inside the cloud. For example, GRE tunnels were dropped not long ago on the GCP. Also, there were some issues on AWS with them as well. When you are using native solution, you will find there is no BFD support, so the failover is pretty slow, up to 90 seconds. You can play with the BGP timers, but will not get you far. And at the end, each cloud has different issues, different approach to the network, which means each cloud has to be treated differently at all. Okay, so how can we overcome those issues that we mentioned earlier? Well, we can't peer directly with the cloud using a VPN and BGP, and we can't use the cloud as the dump layer to switch. It will just not work. What we can do, we can create additional overlay on the cloud using UDP tunnels, because the GRE won't work, and we can use some kind of control plane, again a VPN, which we know very well, to control the clouds. However, the tunnels and the control planes often require custom images, which is no-go for us as well. So let's sum up the requirements that we have set up. For first, we require that there will be a seamless integration with the existing VMs, so no custom images. We must be using pure images from the cloud, pure Red Hat, pure Ubuntu AMI. The zero-touch provision should be done using Cloud Init, as all of those instances are supporting them. We require that we must have full network support from layer 2 to layer 7 with all the protocols in the middle. Our solution should also have access to the cloud native resources such as Azure Lambda or Azure RDS, AWS Lambda or AWS RDS. However, those requirements limits our solution for now only to Linux hosts. And the BSD should be working as well with the Windows at the end, which has pretty limited cloud init support. So let's keep and concentrate on the Linux for now. Okay, we also require that the gateway on the cloud should have access to the rest of the topology using existing tools such as FRR and a VPN, so it can integrate seamlessly with the rest of our topology. Okay, so with all above consideration in mind, and after we've done some R&D, we came to the following solution. We'll use the Cloud Init to configure virtual machine on the cloud. This way, we'll avoid the modification of the virtual machine image. For each deployment, for each VPC, we will create a gateway. The gateway will be built from WireGuard. There will be an FIR on it, the VPN. Also, there will be a custom zero-touch provision. I will cover that a little bit more later. And to connect the virtual machine that we'll create with the gateway, we'll use the generic encapsulation protocol, which will form a tunnel between the virtual machine and the VM. So, whenever we create a new virtual machine using AWS UI, we will add a static user data, which is basically 4 lines of the code, and is the static and the same for all the virtual machine in one location. So it's simple copy and paste. Then during each boot, the layer 2 interface will be created using boot init clause. Then during only first boot, the zero-touch provision will be performed. So virtual machine will call the gateway will create the endpoint on its own, point the endpoint, the tunnel to the virtual machine. The virtual machine will get configuration from the gateway, so it will remove its default gateway default route. It will configure the static IP on its physical interface and create DHCP configuration on the tunnel. At the end, on the gateway, we will periodically launch a script that will clean these endpoints that are no longer in use. So we'll ask the AWS for the IP addresses on the current VPC, and if we have tunnels toward different IP addresses, those tunnels will be removed. We have created that solution, and we have found that the ZTP we created is working pretty good on the Ubuntu, Red Hat, SUSE, and Amazon Linux, so we have covered most of the current distributions. Okay? So
right. So the next thing that we want to talk about, next connectivity scenario, is connectivity with a branch office using EVPN. And the technology stack consists of the mechanisms that we have talked about before. So we've got EVPN, we've got VXLANs, and we have also an encrypted tunnel, such as WireGuard. For our demo, we'll be using WireGuard, and for one of the branches, we'll be using IPsec. So both of these technologies are being in use. And if we have this technology stack, we can provide layer 2 and layer 3 connectivity between branch offices, connectivity with headquarters, with data centers, we can connect to cloud, we can connect to IoT, so basically to the devices, to the resources that are also using this technology stack. Now, in case of branch offices, we can enable it on, for example, enterprise-grade networking devices. So we might have an expensive router to run EVPN and VXLANs, and we can also have some separate firewall to perform the encryption. However, in many branches, such big performance, such big devices are not really needed. And in many cases, we would do good with a server that is running these solutions in CPU, in software. In some cases, we might actually do good also with a mini PC with some extra connectivity enabled. But we actually can go one step further, and we can use consumer-grade routers such as MikroTik, such as D-Link, and such as ASUS, and use an open source Linux distribution that has drivers for all kind of interfaces and wireless devices, and that also allows to install software such as FRR and such as WireGuard. And this is exactly what we did, and we'll show it during the demo, where we installed OpenWRT on a MikroTik router. Now, keep in mind that the connections between the locations, between the branches, are using a WireGuard tunnel or some other encryption, and inside of it there is a BGP protocol session running. This means that we can use the load balancing and the redundancy features that we have presented on the first webinar. So, for example, if we have two connections to the internet, we can use two encrypted tunnels and load balance traffic between them. If one of them fails, the traffic will very quickly fail over thanks to BFD. Now, why would we want to stretch layer 2 to a branch office or between branch offices? Well, to be honest, it is mostly about the flexibility. It is true that we can do a lot with layer 3 only, but in some scenarios, layer 2 will simplify our topology and simplify our configuration quite a bit. So, for example, if we would like for the multicast traffic to be able to be forwarded between branch location in some overlay network, well, we can do that. We just stretch layer 2. If we want to use some services which are basing the high availability on layer 2 connectivity, well, we can stretch layer 2 again between the branches. If we would like, for example, to group users into a single network and do not care into which location the user is connecting to, stretching layer 2 will also help us with that problem. And finally, we can use VRFs to create all kinds of different logical topologies where we can, for example, force some of the traffic to be flowing through a specific device. So here we do not allow direct connectivity between blue and green overlay. We force the traffic to go through a physical firewall in the central location and only then to the destination overlay network. So we've got much more possibilities that can be very useful in various connectivity scenarios. So this layer 2 extension to branch is something that in many cases is very beneficial.
Okay, but what if we have a device that will not be supporting a VPN or a WireGuard, or worse, what we have a device when it can be flashed with an OpenWRT. Sometimes the device can be locked, sometimes the device is lacking features. What can we do that? Well, in most of the cases, that device already is supporting MPLS plus GRE plus BGP, and we know that the FRR is supporting those protocols as well. We can add the IPsec to protect the payload, as the endpoint device will not be supporting the WireGuard as well. So we have the same solution. On the hub, we redistribute the layer 3 VPN with the MPLS between layer 3 VPN and between AVPN. So everything that comes from the legacy device will be redistributed into AVPN VXLAN encapsulation and in the different direction as well. However, there is one drawback of that. The Linux does not support VPLS, the layer 2 MPLS VPN, so we won't be able to stretch layer 2 networks towards legacy devices. We can exchange the Linux hub with the FreeBSD hub, which is supporting layer 2 VPNs, VPLS, but it's outside of the scope of this webinar. The plus of this solution is that since we are doing all the redistribution on the hub, there is no need to change the configuration of the different endpoints. Everything is being done on the hub. The original endpoints still are supporting either only a VPN and VXLAN or layer 3 VPN and MPLS. We tested this solution and we know it is working on Juniper SRX. We know it is working on MikroTik and others such as Cisco.
Now, the last connectivity scenario that we want to talk about is connectivity to edge servers and to IoT devices. And the solution here is again the same technology stack with EVPN, VXLANs, and some form of encrypted tunnel. And the thing is that these technologies can be supported inside of a CPU using only software, and it can be run on different CPU architectures. So for example, in case of edge computing servers, we can use Intels and AMDs. In case of IoTs, we can use ARMs, we can use MIPS, PPCs, so different CPU architectures. So it is perfectly possible to run this solution on a single board computer, such as Raspberry Pi. Now, in case of IoTs, obviously there will be some limitations. In case of single board computers such as Raspberry Pi, will be limited by the CPU, which usually isn't very fast, but it will mainly limit the throughput through the encrypted tunnel. And usually the IoT devices aren't very talk active, or at least they shouldn't be very talk active. Now, when it comes to low amounts of RAM memory, it will lead to limited amount of routes that can be processed by the BGP protocol. Now, again, in case of IoTs, usually they do not have to talk to every possible MAC and IP address in the data center, which means that we can use route aggregation and route filtering to send information in the BGP protocol to IoTs only about those machines, only about those resources that are needed for the IoT to work correctly. Obviously, in case of edge servers, we do not have these limitations with CPU and RAM memory, but it is also a good idea to filter the routes so we have more security. All right. There's one more thing here that we need to remember about, and it is that the encryption tunnel that we are using will support client-to-site VPNs, because the IoTs and the edge servers will be the site that will be initiating the creation of the tunnel. And also, the tunnel needs to be able through network address translation. And this is because, for example, if we are using 3G or 4G modem to connect to the internet on an IoT device, in many cases, the ISP will assign a private IP address, and only then the packets will be translated to a public IP address and forwarded to the gateway. So, working through NAT, NAT traversal is a must in this kind of scenarios. Now, there's one more thing that we have on the logical diagram over here. It is not directly connected to IoTs or edge computing, but it shows that we can use the route manipulation and ACLs in order to restrict connectivity between the devices that might be located in the same overlay. So through route manipulation, we can, for example, allow IoTs and edge servers to talk to resources in the data center, but we could also prohibit them from talking to each other. So this is one of the use cases that might be useful and will be quite similar to private VLANs on Ethernet switches.
Okay, now it's time for the demo. Let's talk about the demo agenda. First, the demo will be a little bit longer than usual because we have a lot to cover. We'll start with the presentation of the topology. We'll describe the communication between the underlay and overlay and communication towards the internet. We will also discuss how to extend the overlay to the public cloud as well. We will discuss service migration from the local DC to the AWS cloud using VRRP protocol. Then we'll discuss how service can be migrated using BGP as a service solution. We will show how the resource in the data center can access native AWS resources such as RDS. And at the end of the first part, we will show how AWS VM can be deployed using described earlier solution with ZTP and Cloud Init.
Right, and during the second part of the demo, we will show that we can use this MikroTik router with OpenWRT installed on it, and we will have an IP camera wirelessly connecting to this router. And this wireless camera should be reachable over layer 2 from the data center. So we should be able to use ONVIF multicast discovery to see the IP address of the camera. We will also simulate a LAN user that is trying to access the internet, and the user would be connected to this router. However, the communication with the internet will not be direct. The traffic will be forced to travel through data center, where there is a central firewall that has traffic filtering configured on it. And finally, we'll show an example with a legacy device with MikroTik running its original software that is able to establish IPsec tunnel with MPLS-based L3 VPN to the hub location. Okay, and the last connectivity scenario would be an extending overlay to an IoT, which in our case is an Orange Pi Zero device that is connected to the internet through a 4G modem. And to this device we've got an OLED screen connected. So we'll try to get some reading from this Orange Pi, and we will also try to send a command that will display something on the OLED screen.
Okay, so this is the topology in detail. I agree it's pretty complicated. We'll split it into parts later on the next slides, but just a quick summary. On the left, we can see the resources that we created in the aerial webinars. So we have a bare metal server with virtual machines with both VRFs red and green. Then we have the server with containers, also two VRFs red and green. Those containers will be later used to access cloud resources. Then we have resources placed on the AWS cloud. We have a hub, we have a gateway, we have a machine with HTTP service VRRP as well, and we have native AWS resources database. On the right, we have the IoT devices and branch office devices, and we have here there is a OpenWRT devices serving a branch office. There is an IoT device, and we have a legacy MikroTik device that will be using MPLS over GRE. At the bottom, we have, as before, two leaves, one spine. We have added the SRX device to allow internet connectivity. Okay, so this is a simpler lookup. We have one network on the red VRF that is stretched across data center, AWS, and as well as the branch office on the OpenWRT. We have native network on the HWS, which will be used to access RDS. And in the VRF thread, we have also a MikroTik device with the original software serving one network, which will be advertised using L3 VPN. At the bottom, we have VRF Green, which is also distributed to the branch office with the help of the OpenWRT. The VRF Green is also present in the data center, and the VRF Green is also present in the Orange Pi, which is acting as an IoT device.
Alright, so on this slide we have all of the relevant containers, virtual machines, desktops, cameras and other resources that are connected to all of these locations. And on the first connectivity example, what we are trying to do is we want to be able to access internet from a virtual machine running in the data center in the red VRF. So using default gateway, it will send the packet to its FRA router running on the same host as this virtual machine. Then FRA router will check its routing table and see that a default route is reachable through a spine device through VXLAN tunnel. And further, the spine device should also have a default route in its routing table and see that it can forward packet to SRX device to the firewall, which will further forward it to the internet. Now, this all relies on the fact that this default route is present in all these routing tables along the way. And we do not want to use the static route, so instead of that, we are going to use EVPN Type 5 routes in order to advertise this, this default route. So this is the thing that we want to show, this advertisement, and then the connectivity, the ping from VM to the internet. So let's start by showing you the screen where we have the overlay scenario. And here we've got the Alpine Red, which is the virtual machine. Here we've got SRX firewall, to which I will need to reconnect real quick. Alright, and we also have on the right a spine device. Now, what we would like to check in the beginning is whether or not we've got this automatic route advertisement configured. So we might start on the SRX device and see what is, what is the routing table there. Sorry about that, 1 second. Okay, yeah, show route. So basically we are checking the routing table of the firewall, and we can see that indeed it has some static route, and it is the only static route in this example. Now the SRX should advertise this route using dynamic routing to the spine device. So it has direct connection to spine device using one of its interfaces, and we can see that indeed it is advertising default route into the OSPF. Okay, so let's take a look at the spine device, whether or not it receives this advertisement. Right, so what we are going to check, we are going to check the red VRF routing table, which has OSPF protocol enabled in it. And indeed, a route from OSPF protocol that can be used to reach the internet. So everything is fine so far. Now the spine device has the responsibility of taking this default route and advertise it further to every router running our overlay, so all of the FRR servers. And this advertisement will be done using EVPN Type 5 routes that we have talked about during the presentation. So we are looking at all of the routes that are being advertised to the FRA router where the VM is located at. Alright, and this is the route that we are interested in. This is a Type 5 route, and it is the default 0/0 prefix. So yeah, it does perform the advertisement, which in turn means that we should also be able to see this route on the compute server itself, where the virtual machine is running. Alright, so let's see the routing table in the red VRF.
You are inside the VRF.
Oh, sorry, 1 second. Yeah, so let's try it again. I was inside of a virtual machine. I want to check the route on the host. So IP route over here, And what we should be able to see over here, the default route that is going, that is going through this IP address. This is the IP address of a loopback on the spine router. So everything is in order over here. So let's hop back into the virtual machine and verify whether or not it is able to ping the internet. So we are going to try to ping the Google DNS server, and we should see that indeed it is able to reach it. And just to be sure, we can also verify if this traffic is actually flowing through our SRX firewall. So we are going to view all of the stateful firewall sessions that have the destination prefix of 8844. And indeed, we do see traffic from this IP address. This is the IP address of this virtual machine. And we actually can see that some form of network address translation is being performed here, the source network address translation. Usually we would see a public IP address, but in our lab this is translated to another private addressing, and it receives a public address somewhere further along the way. But basically we see that this connectivity is working as expected.
Okay, so let's move to the next part of the presentation. Now we'll talk about the service migration from the data center to the cloud. We will cover two examples. The first one with the VRP. We have HTTP server running inside the container in the DC. It has VRP with the virtual machine on the cloud. There is a HTTP server as well. This is the master, this is a slave. So from here, we'll ask the web page, we'll see it comes here, and then we'll start to migrate to the cloud. Okay, first let's ensure that we have running VRP service. Yes, it's running. Let's check if there is an IP address on assigned virtual. Yes, we can see that there is 10.1.0.20. This is the virtual IP address. So VRP is active on the data center on the container. Now let's start watching the web page. And we can see that the www is being served from the container. Now let's start watching the logs on the cloud. Okay. Journal. Okay, the cloud is in backup state. So on the master, let's stop the VRP service. And we can see that immediately the IP address has been moved to the cloud, and we are serving the web page from the cloud as well. Okay, but let's, just before we move to the BGP, let's try the opposite direction. And it's being done. We move the service back to the data center. Okay, but well, the VRP is not a state-of-the-art protocol. It's being used, but a lot of people has moved to the BGP as a service solution. Well, we can do that as well. Let's first ensure there is no BGP running on the cloud. And let's say that we want to serve something from the web using web page, using 6.6.6.6 IP address. So we are doing a curl here, trying to connect to that IP address. Okay, so since we are not advertising anything, there is a timeout, there is no communication. But what will happen if we first start the BGP and we'll establish BGP peering with the gateway on the cloud? Okay, the state is established, we received already some routes, and now let's advertise the IP address from the cloud, from the DC, from the cloud towards the gateway. And we can see the curl running on the DC is getting responses. What we have done here is, here we run a GoBGP instance, we peer with the gateway on the cloud, we advertise loopback routes. So here a request goes via the hub, via the VPN, towards the gateway, and here towards the AWS resource. Okay, so this is BGP as a service. Now let's move to the accessing native resources. First, let's take a look at the topology. Okay, so it's not being updated. Okay, so yeah, we have Elixir containers on the data center, which has MySQL client, and we have created database serverless on the AWS in 2 zones, and we would like to access that resource from the data center via the hub, via the gateway to the cloud. So first, let's check if the instance is up and running. Okay, we have database, we have cluster, it's fine here. On the container, let's check if can access the DNS service. It has 2 IP addresses, in private range, it's no internet. So now let's launch the MySQL client and see if we can get a response. Well, we do. So we run the MySQL, we connected to the resources on the cloud, we did an SQL query select version, and we got the response. Okay, so we can now access native resources such as an RDS without much of an effort. Everything is being taken care of by the FRR and our topology. Now the next part is deploying the AWS VM on the cloud. So what we will do, we'll go to the UI, we'll click to create the EC2 instance. The EC2 instance will be deployed with the CloudTiNI configuration. It will create first the interface we talked about earlier, the layer 2 interface. Then it will hit the zero-touch provision on the gateway. The zero-touch provision will create the other endpoint of the tunnel here. Then there will be a network configuration on the virtual machine, which will remove the default route towards physical interface and add the ACP configuration toward the VMC. So, okay, let's see how it will work out. Now we have an AWS UI. We can create, to speed up things, we'll use an existing template. Again, this template does nothing. Well, let's select here the Red Hat, not the default Ubuntu. This template is just predefined. There is nothing special. There's SSH keys, of course. There is a VPC assigned. The most important part is at the bottom. We have here user data, which pretty means that we create the layer 2 interface. We assign a MAC address that is based on cloud instance ID, just to easy find it later. And then we run the zero-touch provision. Okay. We launch the instance. Okay, we're seeing it's being created. It's a pending state. Now let's go back to the logs. Okay, so here on the compute 1, we have DHCP running in the network that is stretched to the cloud. So as soon as the instance will boot up, it should ask for the DHCP address. And when we get the DHCP address, we'll try to SSH from the Elixir container on the different bare metal server in DC machine. Yeah, it can take a little bit of time, so we just have to wait right now. Yeah, HWS can take some time. Okay, we see that we have DHCP discover. The MAC address 5A28 is the same as the instance ID. So we have assigned the IP address 10.1.0.98. Okay, so let's try to SSH there. The endpoint is 98. And we are here. Let's see if we have connectivity, how the network is being configured on the Red Hat. We can see we have default HT0 connection as well as the VMC virtual interface that we create during boot up scripts. The IP route should show us that default route is going through our gateway, not through the physical interface. So we should be able to access all DC resources as well as to go to the internet through the DC gateway, through the DC firewall. Okay, so this sums up the cloud part of the demo.
Right, and we have two things left to show here. Now the first part will be about OpenWRT, where we have an IP camera wirelessly connected to the branch router. Now this wireless camera receives IP address from DHCP server, but the DHCP server is located in our data center. Now, what we'll be trying to do is we'll try to use ONVIF discovery that requires multicast to see what is the IP address of the camera, and then we'll also try to see what the camera is viewing, whether or not we can actually communicate at layer 3 with it without problems. And we'll also show commands through which we'll see that that the MikroTik router running original software is also visible to the overlay network, and the routing tables are properly filled out. So let's start this example by logging onto this OpenWRT device. Yes, we are already here, and let's see really quickly what is its configuration. So first off, we'll check what are the stations connected to the Wi-Fi network. So the Wi-Fi still works, even though we flashed different software than the original MikroTik operating system. And there is a single station connected. This is this Wi-Fi camera. All right. Let's check out the CPU information because we want to verify whether or not this is indeed a MikroTik router. And yes, originally it was MikroTik. Now this is OpenWRT with CPU architecture of MIPS. What is also interesting is the amount of memory on this device, which is 60 megabytes. And still with not a lot of memory, we are able to run FRR, EVPN and WireGuard encrypted tunneling without problems. Okay, so we talked about encryption using WireGuard. So we can verify that indeed we are having a WireGuard tunnel established to a location in Amazon. So the hub for our VPNs for the encrypted tunnels is in Amazon, in this lab. And finally, one last thing, the MTU configuration on the WireGuard tunnel. We can see that we have set it to 9,000 bytes in order for it to be able to encrypt large packets, which then it will have to fragment for them to be sent through the internet. Okay, and one more thing that we want to check before we try to use multicast is whether or not we are actually using EVPN over here. So I'm accessing the FRR console and just showing whether or not we have some BGP sessions established. And we can see that indeed we've got some sessions for unicast addresses through the WireGuard tunnel, and some IBGP sessions for layer 2 connectivity for EVPN directly through the tunnel to the spine device, which acts as the root reflector. So everything seems to be in order here. Okay. Yeah, and the first thing that we are going to show actually is the connectivity scenario from a user to connected to this branch router to internet. So we actually do not have a laptop connected to this router. So instead of that, we are going to use an IP address that is configured on one of the interfaces in the green VRF. So what we are going to do, we are going to try to ping from the green VRF, from the bridge users interface, a location somewhere on the internet. And what we can see that indeed we are able to get to this IP address. However, remember that this traffic is actually flowing through a firewall. There is a central firewall on which we have security policies configured, and there is a security policy that should block traffic to 8.8.8.8. And indeed, this traffic is not flowing. We can verify it on the SRX device. Just to make sure, we can see the configuration of the security policies over here. And indeed, the first rule will block traffic from this IP address on the OpenWRT device to the internet to 8888. But all the other addresses are permitted over here. Okay, so we've got connectivity from branch to the internet. Now let's see if the connectivity between data center resources and the IP camera is also possible. So, in order to do that, we will enable TCP dump on the OpenWRT because we are going to try on-with multicast discovery. So we are interested in packets that are either destined to this MAC address, this multicast IP address, or directly to the camera. So let's see. Okay, there is actually a stream flowing right now. So instead of we will be only interested in the multicast packets. All right, and let's try from the COMP6 device. This is a desktop that is connected to the data center. It is COMP6, so it is a bare metal server. It doesn't have FRA routing installed. It doesn't have any extra routing daemons. It is just, plain bare metal server without anything extra on it. And using this tool, we'll send multicast packet that will try to detect the camera. And indeed, we can see that this multicast communication was possible because the camera was successfully detected, and this is its IP address. All right, so this works without a problem. We have the multicast capability, the link local capability, without configuring multicast routing. So the next step would be to also check whether or not we are able to see what that camera is looking at. So this is just simple connectivity, nothing special about that, but we will actually need this for the next step of the demo where we present the IoT. Okay, and it works. So the camera is looking at the IoT device, at the Orange Pi, which has an OLED screen attached to it. And the DAC is very important here because it supports this structure. What we'll try to do further on is to display something on the OLED. So we will get back to that shortly.
Okay, but before that, we'll cover one more topic in our presentation, which is legacy access of the using MikroTik original software. We got disconnected from the hub, it happens. Okay, so first let's go back to the topology and see what we'll be doing. We'll be having a hub here, and we'll be having a MikroTik, which has original software. There is a GRE plus IPsec plus MPLA layer 3 VPN with the BGP help as well. All together is here configured, and the hub will be redistributing those roles towards the rest of the topology. Okay, so let's first check the configuration of the MikroTik. We have one routing instance, VRF Red. It has the same route target as the AVPN, so that's why the redistribution is possible. Of course, we have a JRE tunnel. The JRE tunnel has a DMTU assigned. It has the address of the hub at the endpoint. There is an IP secret which creates the IPsec policy transparently inside the route OS. This is the pre-shared key. So since we should be having BGP session, we should be receiving routes as well, and we can see we are receiving all the routes from the hub, which is the IP. This is the IP address of the hub, and this is all the routes from the rest of the AVPN topology. Okay, so we can do one more thing on the MikroTik device. It has its own IP address assigned, and let's see on the hub how this IP address is visible. And we can see on the hub that we are receiving this using BGP protocol, and we are seeing that this is in the endpoint is in the VRF default. However, we have to push label 16 so we can differentiate between VRFs between MikroTik and the hub. The configuration of the hub is pretty simple here. So first, we have added the MikroTik ABGP session inside the BGP configuration. We add that BGP session to the IPv4 VPN family, and inside the VRF, we have added VPN configuration import-export, as well as the route target and route distinguisher. All this required, and label VPN export to assign the VPN labels and PLS labels. All that is needed, and with that, the redistribution between the AVPN and layer 3 and PLS is being done directly on the router. So all other endpoints are seeing just pure AVPN configuration. So this sums up the legacy part.
Yeah, and there is one more connectivity scenario that we wanted to talk about. And this is connectivity with IoT device with this Orange Pi that is connected to the internet through a GSM, through 4G modem. And we've got an IP camera looking at its screen, so we'll try to issue some command that displays something on it. Now, in order for the command to reach the IoT, it will actually have a few steps to travel. So we'll send the command from COMP6, which is in the data center in the red VRF, and the IoT, we've put the IoT in the green VRF in order for it to be a little more complicated. So the packet will travel to FRR, then it will be forwarded to layer 3 gateway at Spine. It will go through the firewall, so we can limit the connectivity on the firewall without any problem. Then we've got Spine in the green VRF, FRR, and this is actually FRR on the IoT, on the Orange Pi already, and then to an IP address configured on its logical interface. So this is the connectivity scenario, and we'll see in a second whether or not it works as expected. All right, so again, let's start with verifying the configuration of the Orange Pi. So we'll take a look at its CPU architecture, and then we'll see that it is indeed not an Intel, not AMD, it is ARM. Okay, the next thing that we might want to check is the IP route. This is the main routing table, and what we can see here is that the default route to the internet, the connectivity with the internet, is through some USB device. This is the USB 4G modem. Okay, next thing to verify is that we are encrypting the traffic and not using unencrypted VXLAN tunnels, and the hub, again, the Amazon virtual machine. All right, and the last thing, just to make sure we can check the FRR, whether or not it is being used. So I've accessed this console, and we can see in the BGP sessions that indeed we've got EVPN address family, and we are using it to have this layer 2, layer 3 connectivity. Okay, so the IP address with which we are trying to connect is located on this logical interface, green L2. We can see that it is 10.2.103.1, and on this IP address we are running a service, a simple HTTP server running using Python. So we can verify that indeed there is a service listening, and we've got a service listening on all of the interfaces in the green VRF. This means that if a packet would arrive in some other VRF or on the main routing table, it would not be able to access this service. It is only for the packets arriving in the green VRF. And this is actually quite simple to accomplish. It is quite simple to put a service in a VRF, because all we need to do is we need to issue a command IP VRF exec. Then we specify the name of the VRF, and finally the command that is starting up the service. So nothing complicated over here. Okay, so the service is running, the service is ready, so we can try to communicate with Orange Pi from a desktop computer that is connected to the data center. So first off, we can try to check whether or not we can read its temperature sensor, and indeed we've got some response. So it is working as expected. Now, what we might also want to do is we might want to send it some command. Now, this command will try to display something on the OLED screen, so I will also need this view from the camera. So I will issue the command and then switch to the camera. And what we can see that indeed there is something happening. We issued a command, in our case this is an OLED screen, but it could be, for example, manipulating some servo, opening something up, starting up an engine or stuff like that. You know, IoT, what the IoT are used for. So it is working as expected. Now we can also verify one more thing. We can verify whether or not we are actually going through a firewall, that we are forcing the traffic to be pushed through the firewall in the central location. Oops. Okay. Right, so in order to do that, I've logged onto the SRX device, and what I will be interested are the sessions to the Orange Pi. Right now, nothing is flowing, but if I issue this command again, we should see that indeed there is a session, and we could limit connectivity only to those devices that should be able to talk to IoTs, and in the other direction as well. We could protect IoTs or edge computing servers from accessing some of the resources in data center, in cloud, or some other locations. Okay, and this actually concludes our demo. So just a last command issued to the IoT, and it works as well. Okay, so it is time to summarize what we have said here today, and we'll try to make it quick. So I will not talk about every pros over here because we have mentioned them during this presentation, but hopefully you are able to see that we are able to create various logical layer 2 and layer 3 topologies with which can connect resources that are located in dispersed locations. They are not in a single locations, but they can be in various parts of the internet. Now, it is true that we can do a lot with layer 3, but we can do even more if we also have this option of layer 2 connectivity. And it might be important in scenarios where we are migrating some services between local DC in the cloud. It can be very useful when we have AJ solution that requires layer 2 connectivity. And it is quite useful for various scenarios in case of enterprise networking where this layer 2 connectivity can be quite helpful. Now, if we need only layer 3, then EVPN type 5 routes can also be able to help us with that. For the traffic encryption, we can use anything that can encapsulate UDP, that supports IP fragmentation and reassembly, and we also need to remember about this network address translation traversal. And finally, the last point, probably the most important here, is that this solution, the software components are based on open standards. So they are interoperable between devices from different vendors, and we can also run it on open source software. And also it can be used on low-end devices using various CPU architectures.
Okay, but as we all know, sometimes there are drawbacks, and well, what we have discovered is what we have shown is this configuration is pretty powerful. However, it is complex, so sometimes it requires advanced network knowledge as well. Sometimes the MTU has to be taken care of. Most of the time, the MTU path discovery works fine, so nothing is needed. Everything is being auto-discovered along the way. However, MTU is something that we need to be kept in mind as well. There is no FRR support, no VPLS support, not the FRR, so there will be no layer to support for legacy devices. For FRR on Linux, on BSD, the VPLS is working just fine. And this solution works mostly with the cloud init enabled devices, so the supporting for the Windows on the cloud will be pretty much limited here. We also encountered a lot of problems. I will try to sum the most important of them. So on the OpenWRT, the current stable distribution is being based on 4.14 kernel, and this kernel does not yet support full set of the AVPN features. There is no layer 2 MAC address learning, so the ARP requests are being flooded towards the rest of the topology. This will be fixed with the next release, hopefully this year, so it's a short-term problem. There are some issues with the FRR, so we have to end it with the exact branch, subset patch of the FRR, because the previous version has some issues. The newest one introduced a different issue with the Ethernet segment, so we have to end it in the middle. So of course, the guys at the FRR are aware of those issues and are being fixed or are already fixed in the master branch. Also, the one thing that is pretty obvious but complicates a lot, each Linux configures its network differently. Even when we are talking about the Linux with the sysconfig configuration, Fedora, SUSE, Amazon Linux or Red Hat, each of them are configuring the network in different way. Some of them has network manager, some of them has script, some of them are based on UDEF events. So all those things complicates and create a lot of exceptions in the zero-touch provision and needs to be taken care of.
Okay, and with that we would like to summarize what we have learned about not only on this webinar but also on the previous one. And this is that we can use open standard technologies that are widely available, and we can use them to deliver quite an advanced networking solution. So we've used some of them that we have used were IPv6 link local addressing for auto configuration, neighbor discovery, BGP, unnumbered sessions. We have used BFD for very fast failover, ECMP for load balancing, Cloud Init for automatically configuring new VMs, and could be also used for servers. We used VXLAN for layer 2 connectivity, and VRFs for advanced architectures with layer 2 and layer 3 networks. EVPN, because we didn't want to manually configure all of those tunnels and manually fill out the bridging tables. We've got GRE, NPLS, and IPsec for legacy branches. And we could continue with this list a little bit more. But basically, hopefully, we were able to show that it is indeed possible and quite beneficial. and also that it is beneficial to run a routing daemon such as FRR on a server, because all of that would not be possible without this solution, and we are very helpful that such software as FRR is out there at the people's disposal. Now, in today's webinar, we've also showed that EVPN with VXLAN tunneling can do a great job for providing layer 2 and layer 3 connectivity between remote locations, and also that even though public cloud networking is limited in most of the cases, we can still achieve full connectivity between the virtual machines inside of the cloud, and also between virtual machines in the cloud and in local data centers with the use of overlays. So we hope that you have enjoyed this webinar series. We have certainly enjoyed creating them. And now let's see if there are any questions.
Okay, so far we have two of them questions. Let's go with them one by one. The first one is, have you tried different clouds such as Azure or GCP? Not in the demo, but we are working on them during R&D. There are issues. As said before, Azure has different network, GCP has /32 prefix. Those issues create a little bit of more work, but they are working just fine, and the VXLAN or the GenEve are typically just a UDP traffic for the underlay cloud, so it should be working just fine without any issues. However, with the lack of the time, we didn't manage to add it to the demo.
Okay. All right, so let's see the second question. Would Arduino board also be able to run EVPN? Well, we have, that's true that we have used a quite powerful IoT device, which was Orange Pi Zero, to do the EVPN and WireGuard. And in case of Arduino boards, they have, some of them can have really low RAM memory, like 8 kilobytes or something like that. With that low amount of RAM, we would not be able to do that. Also, the CPUs are far less powerful. So in this kind of cases, what we would recommend is to use, for example, OpenWRT router as the gateway for them. So the OpenWRT router would be able to stretch layer 2 connectivity to an overlay network, just like we have seen it happen using leaf switches who are stretching the connectivity to a server, to a bare metal server. The concept is exactly the same. So with every device that cannot support the EVPN directly, we can pull it into an overlay using layer 2 gateway. Yeah, and also we could use an USB device to extend this to IoTs that do not directly talk on IP. So for example, some IoTs such as LoRa, such as Zigbee, such as Z-Wave, such as other IoTs that have different kind of connectivity requirements. But we could, talk with them, read their sensors through a device such as Raspberry Pi, for example.
Okay. The last question so far is about the gateway redundancy on the cloud. Okay, that's a big topic, because what will happen if the gateway will fail? The machines on the cloud will have lost the connectivity. Of course, we can spawn a different machine, which will take IP of the previous one, restore the tunnels, and continue working. However, this would require to call the API of the cloud, which is an issue because the API can be slow. With the AWS, we are lucky. Such a readdressing of the second gateway would take seconds. On different cloud, Azure, it can take minutes. So this is a cloud-native solution, but it won't work well. So I think the best solution would be to create a second tunnel on the machine. To keep things simple, we'll add the bridge connecting those tunnels, so we'll have still a simple one IP address with two directions to both of the clouds, to both of the gateways on the clouds, and we can keep running VRRP between those gateways. Since we are having full layer 2 connectivity inside the overlay, we can run between gateways VRRP, so if one fails, the other will take over. We can stretch make the VRP stronger with the help of the BFD, so the failover will be even faster. Of course, we can do some proprietary solution with the active standby tunnels, but this won't be as open as we would like to be.
Okay, and we've got one more question, which is the setup is it's a pretty complicated project. Did you have all planned from day zero, or you had to adapt as you were going along? So we did work with EVPN quite a lot, so we did know the capabilities that it has. However, there were some issues, there were some problems, there were some, dead-end alleys that we went into and that we had to back up from. So it wasn't as we had everything planned out from day zero. We actually needed, to change some of the approaches along the way because, indeed, the solution does consist of many different parts that need to work together correctly, and this was probably the most important and quite difficult to make them work as we wanted them to.
The other next question is: does this Allotion supported for a VPN over MPLS? Please go.
Yeah. So EVPN generally is supported over MPLS. EVPN is a protocol that can run on MPLS, on VXLAN tunnels. There are drafts for other tunneling protocols as well. However, in case of these solutions, we are heavily using FRR, software routing daemon. And in this scenario, so VXLAN is supported, it works very well, and we didn't even try using MPLS. I'm actually not sure if it is supported directly on FRR or not. However, MPLS is a little bit more complicated, and I think it would be our recommendation that if you can use VXLANs instead of MPLS, you do not have advanced connectivity requirements that would make MPLS worthwhile, then you can stick to VXLANs. If you are talking about data centers, VXLANs are usually enough. Now, if you wanted to, for example, use this connectivity through an ISP network and you were the ISP with full control over the MPLS, then you might play with it as well. It should work, it should work without much problems.
If multicast, next question is multicast support requires a VPN native multicast route type? Inside the layer 2, inside one stretch network, there is no problem, as we can see that the multicast is being forwarded correctly without any issues. Between networks, we can use multicast protocols agnostic to the VPN, so it will be terminated on the server and propagated further. So I think it would work without native support of the EVPN. I'm not even sure.
Yeah, there are some drafts for EVPN that do provide connectivity for multicast traffic. However, in this demo, we did not explore them. So to be honest, we're not sure if FRR could handle them. If it does, I don't think it supports, type 6 or type 7 or other routes. I think it stops currently, at least, at type 5. So we've got the prefix advertisement, but there is no support for the drafts. At least I don't believe there is for the drafts that talk about multicast routing. But as Adam said, in case of layer 2 stretch networks, we can support multicast directly through layer 2 connectivity. And I think that is it when it comes to the questions. If anyone thinks about the question that is important for them after the webinar, you can contact us as well. We'll try to help with that. Oh, there's one more question.
Okay, what about the controller to all of that? Not yet, but yeah, it would be nice to have. But one more thing that is important, the FRR is using plain text configuration. So everywhere we're trying to keep as open a solution as possible. So at start, we can use plain Ansible to do a lot of automation here, because using a template, we are showing that in the first of the webinar, with a simple template, we can populate endpoints with the FRR configuration or populate routers in the middle with the FRR configuration, and the rest will happen automatically as the FRR and the AVPN will take over with the configuration. We can limit the route advertisement with extra configuration as well. Again, simple text file, so it can be easily done and easily controlled from one point.
Yeah, so we didn't even try to make a controller for that. It was not part of this webinar series. However, it would be possible if someone wanted to do that.
And it shouldn't be even that difficult.
Okay.
So let's wait a few more seconds for if any more question will arrive. Well, if not, then in the following days we'll post the configuration and the commands and the demo and the presentation to the GitHub in our Codeline repository. It just needs a few straight up and extra description just to provide the clean code without any internal comments.
Yeah, and with that, thank you very much for taking part.
Oh, stop. One more question.
One more question, let's do it.
Great. What about scaling cloud instance bandwidth limit as opposed to the AWS provided integrated VPC device as a NAT gateway in NetGivu? Yes, but the native device, NAT gateway or Inet gateway scales pretty well. However, we can do a local breakout. That can be easily done without any issues and it will work. However, if we want to direct all the traffic back to the DC, it's not so great because on AWS there is a hidden limitation, not a hidden, but there is a documented limitation that the VPN gateway can do only 1.25 gigabits per second. So it's not that fast. We can go faster using Transit Gateway and using ACMP, but of course we can spread out our gateways with the WireGuard as well and be using ACMP as well there. On the Azure, there is a similar limitation. There are as well some on the Azure there are limitations that different gateways have different pricing limits and you can go faster, but I think up to 2 gigabits, and it will be very, very expensive and it will be cheaper to deploy an instance there. On a GCP, I don't think there is any limitation in the gateway, on the VPN gateway, but again, we can spread more instances and achieve the same with pretty much similar cost at the end.
Okay, so again, thank you very much. If you do have further questions, this is our contact email, so you can send the questions to there. And also, if you are interested to learn more about the solutions, we are also open to have a conversation about that. So thank you very much.
And have a pleasant
evening. We hope you enjoyed this presentation.
Thank you.
Thank you.